A short lecture briefly about high-performance computing. So, in BIN 310 we are going to work on a computing cluster. So what is actually a computing cluster? Well, it's several computers, as you can see here, working together, and then we call it a cluster. So this is a rack, as we call it, with many computers linked together, and they work separately but also jointly in some sense. So this increases the computing power because we can have typically a huge amount of internal memory. So we can perform certain tasks that we may not be able to perform on our own computers. And also, since we have so many computers, we can also do what we call parallel processing to increase the speed. So this is the benefit. And computing clusters are used in all computing sciences, you could say. Biology, computational biology is no exception here. So it's just one out of many. So you will probably come across computing clusters in other fields as well. Let's have a small example here. My laptop that I use every day has 16 gigabytes of internal memory. That's pretty average, I think. It has processors with 8 threads. So it means this is the memory limitation, and this is the speed limitation of my computer. How many threads, how many processes can it run in parallel? In Orion, we have nodes who have up to 1,000 gigabyte memory. So you can see compared to the 16 here. So it's much bigger, right? And up to 80 threads, 10 times faster than this, or 10 times as many threads, I should say. Also, of course, my own laptop, when I'm using it, it uses much of its resources for just being alive, you could say, for the process that always has to run in the background in the operating system, while these ones are stripped of that much more, so they can use the power for computation rather than for administration, you could say. Computers. So we also have a national high-performance computing facility, which is called Sigma 2. And the reason I mention this is, of course, that Orion is local to NMBU. So once you leave NMBU, we'll probably never use Orion again. But it may very well be that you will use Sigma 2 in your future, or something similar, right? And Sigma 2 is actually a collection of several clusters. So Fram, Saga, and Betsy are 3 different clusters, just like Orion. Each of them are bigger than Orion. Some of them are even much bigger, like this Betsy. But using them is quite similar. So the point is learning what you learn here in BIN 310 and using Orion is a very good start for using Sigma 2. I think that I use Sigma 2 myself, and I can compare. It's very similar. Very similar. It's not identical in all aspects, but small deviations. So once you learn to run things on Orion, you have what you need to start using Sigma 2 with little extensions. Let me say a few words about this computer, Betsy, which is the newest one of these, the newest part, you could say, of Sigma 2, and the most powerful one. The reason I mention it is its name. Why is it called Betsy? Well, here is the explanation for it. This woman, Elisabeth Stefansen, also known as Betsy, she was the first female mathematician in Norway. She took her PhD in mathematics in Zurich around the turn of the century, 1899, 1900, together with people like Einstein, for instance. She was at the same institution. I don't know if they were there exactly at the same time, but approximately in the same time period. And the reason I mentioned Betsy is that she actually worked here at NMBU afterwards. So the first years of 1900, she was a teacher here at NMBU. And now Norway's most powerful computer is named after her. You can go to the administration building and see some paintings of her. She was a character, I can tell you. Okay, words we should know. A node is one of these computers in the cluster. So the cluster consists of several nodes, right? And they typically have names like CN1, CN2, etc., where CN is just short for computing node. Nothing fancy. When we log into Orion using this terminal that we saw in the first week, we don't log into one of these. We log into a separate node called the login node. And this is never used for computation, only for sort of administration, login and running small things to check that things work and so on. But the big computing jobs are never run here. If you try to do it, it will be killed by administrators of the system. So it's never used for computing, only simple file handling and testing. So when we log on to Orion using RStudio, we also saw that last week, then we are on some computing node. We should, however, be aware that this year we have a sort of a special solution for RStudio in Bin310. So we don't use it in the way you would ordinarily use RStudio as a normal user of Orion. The Bin310 student users have a special access to our RStudio that other people don't have, and we use that. And this is purely because we are so many, right? We are 60 students here now, and the resources are not unlimited. So if all the 60 students were trying to access RStudio as all other users are, then we will have resource problems there. So that's why we have sort of protected both ourselves and the rest of the Orion users to log in RStudio to some separate servers now. So that are normally not, or they are not really part of the Orion cluster, these servers here. So they are not really computing nodes. They are set up specifically for this course. But ordinarily, you will log in RStudio on the computing node, but we don't use RStudio for heavy computation. So it's only a small node with smallish resources, right? Different nodes have different features, types of processors, and so on. And we will not specify features here in our scripts. So this is for more advanced users. We always use a single node in Bin310 also. And I would say in microbial genomics in general, we do that. It's very, very rarely that we use multiple nodes in computations, because that's only for the very, very big jobs. And microbes have smallish genomes. The data sets we have are not that big, typically, so we don't need that. We can stay on one node, and that's really beneficial in other aspects. The nodes are, however, always grouped into what we call partitions. So one group of nodes belong together in the same partition. And this is usually divided by how much memory capacity they have. So the smaller nodes are grouped together and the bigger nodes are grouped together. I mean, bigger in terms of memory capacity. This is quite typical. And when we when we want the computing job to be done, we have to specify which partition. If it requires a lot of memory, it must be in a partition that has nodes with lots of memory. So you don't specify the node itself when you start a job, which node you want to run your job on. You only specify the partition, and then you will be assigned to a node in that partition. So you sort of compete for resources with the other users, but only with all the other users inside the same partition. And again, in Bin 310, we get a separate partition this year. So we don't really need to think more about this. We will use the same partition every time in this course, because this has been reserved for us. Again, in order to avoid too much interference with the other users. Some words we should know. Each node has a number of processors. So each computer, right? Processors, and each processor has a number of threads. And it's actually this number of threads that limits the speed of the node. Yeah, at least in theory. The processors are quite similar to those in your laptop, so it's nothing special about the processors as such. These nodes are not by themselves very powerful or fast. So the increased speed comes from using many threads in parallel. That's the biggest benefit, I would say. So if you cannot use parallelization in any way, it will be just as fast to do the computations on your laptop. There is no gain in speed in that sense. So to use many threads, of course, the software you use must have this built in. Otherwise, it will make no sense, right? So we should always check this. If the software allows us to use many threads, and this typically comes as an option. We will see this later. So when you start to use a new software you're not familiar with, you should first, or one of the first things you should look up is if it can do multi-threading or use many threads. If not, you should use only one thread, right? There is no point in reserving many threads if they cannot be used. You should also be aware that speed is not growing linearly by the number of threads. So if you compare using one against two threads, it's close to a doubling in speed, I would say. But if you compare going from 40 to 80 threads, if you already use 40 threads and you double it to 80, it's probably not going to increase in speed at all. And this has to do with all the there is a cost by doing the parallelization. So if the amount of parallelization is going too big, the gain in having many threads is lost in the administration of many parallels. You can think of it like that. So it sort of levels off, right? So if you're going from very few to a little bit more threads, gives you a substantial increase in speed. But if you're out here, right, it's almost no point in going further, because you will only allocate a lot of resources, but it gives you little gain in speed. So we will stick to few threads. And in microbial genomics in general, I would say 10 threads. You rarely go about 10 threads. Only for the really big jobs like metagenome assemblies and stuff. Personally, I go to 20, but I never go above 20. I have never done. I have tried it, but it doesn't give much faster computations. Words we should know. A job. Yeah, a job is a computing process that we start. So once our computation starts, it is a job, all right? And each new job gets a job identifier, a number, job ID we call them. So that it's simply an integer, a big number that identifies our job. And this is a number we need to sort of store in a sense, or we need to remember in some cases. We will see. We always submit a request for a job to a queuing system, and this is special with the computing clusters. They always have this queuing system. And this is for efficient use of resources, right? Because jobs don't necessarily start immediately once you submit them. If there are many users at the same time, there is no capacity for running all of them at the same time, then you are in the queue. And this queuing system makes certain that resources are used efficiently, right? So this computing cluster is running day and night, right? So even if people go home from work in the afternoon, the jobs in the queue will still be there and run throughout the night. On Orion, we use a queuing system called Slurm, and this is exactly the same as Sigma 2 is using, so that's nice. The queuing system decides which nodes we will be using. So we just specify the partition, and then the queuing system decides which node we get. We may interfere with it, but we will try not to do that, because then the queuing system is sort of less efficient. But there are cases where some nodes are misbehaving dramatically, and then we can exclude them. That's the simplest way of interfering here, excluding certain nodes. We may come back to it. Hopefully not. As users, we have to specify how much memory do you need for your job, which partition do you want to use, and that of course has to do with the memory usage, and then also specify how many threads you will reserve. So memory and threads is something you always have to think about. Partition is, as I said, since we in Bin 310 will have a separate partition, this is sort of given to us. We don't change this throughout this course. But later, when you work on Orion or Sigma 2, you will have to decide which partition you want to submit your jobs, and that has to do with how much memory they need. So also please remember we are many users here, so never ask for much more memory than you need. And this is also for your own benefit, because if you ask for a lot of memory just to be safe, you will have to wait longer in the queue, right? Because then you have to wait until that amount of memory is available. And that can take a long time, right? So it's silly to ask for a lot more memory than you actually need. If you have a small job that uses little memory, you can slip into the queue and run it fast, right? Because there will probably be some smallish amount of memory available quite soon, instead of waiting for the big memory allocation and then not use it. That's really stupid. So for yourself and for others' sake, try to minimize the memory usage. At least don't ask for super much memory until you know you really have to. I should also say that if you ask for too little memory, your job will be killed. If it requires more memory than you asked for, it will be killed. So you have to start it again, and that's also bad choice then. But we will come back to this. Files and folders. So when you log in to the Orion, you always log into your home directory, your home folder. You have a home folder, and this is always found under this address here, /mnt/users/ and then your username. The username is the name of your home folder. So please, I know that many people these days are not used to the file tree hierarchy that we see here, because you see everything as a desktop with icons, right? You can just move around the icons, and you never get the feeling that there is actually a hierarchy of files and folders, and that it is so on all computers. If you have a Windows or Mac, it's exactly the same, but it's just hidden for you. The top of the file tree is always /, right? And sometimes your home folder is listed with a different path here, because there are actually several alternative paths leading to your home folder, but this path will always work to your home. This shell variable here, we saw it in the first week, contains this address, right? And you have up to 200 gigabyte of data that you can store under your home. And that should be plenty for Bin310, because we will try to stick to smallish examples and smallish data sets, and you will not really store the data on your own home, because I have stored them. You can use them directly where they are. You don't need to copy anything. So this should be more than sufficient. In addition, you also have what is called a scratch directory. All users have this. And notice the address is almost parallel to this one up here. So instead of users, it's scratch with capital letters. And then again, your username. So you actually have sort of two homes, you could say. One is a proper home and the other one is the scratch. The shell variable scratch is just an alias for this, just as home is for this one. And the point with the scratch is that here you store what we call primary output from the computations, because some of these computations will result in a lot of output. And if you're, in some cases, this output can be actually too big for this 200 gigabyte. So then we store it on Scratch, because there we have up to 500 gigabyte. But there is no backup. So if things are lost from Scratch disk, it's lost forever. The home is backed up. So if something happens here, you can retrieve it in theory, but not here. So this is meant for sort of temporary storage. So please remember to delete all results from Scratch, because the idea is that you copy all the output to Scratch, and then you copy this whatever you require from this primary output back to your home, which is usually just a small part of it, right? Because these softwares, they output too much. We only are interested in a smallish part of it. And then we copy the files we are interested in back to our home and delete the rest. We may also use this temporary folder here. And that is this shell variable that is the alias for that location. But this is not something we use sort of, this is something we just give as a temporary folder to some software, and the software uses this for some temporary computations and deletes it again. So we never sort of copy things to this folder ourselves. It's for temporary folders for software. We may see it. It's not something we use all the time. This one we use all the time, home and Scratch. But this one we will only see on rare occasions, I think. Yeah, some software tools allows you to specify this temporary folder. That's when we use it. So, just a few words at the end on how we work. There is no graphical interface here, right? And this is the same for all these computing clusters. This is a waste of resources to run this. It takes a lot of resources to run a graphical interface. So we need the command line, but we have sort of the RStudio as sort of a graphical interface, right? So it is, at least to some degree, something we recognize then. But we will use the command line, and that's how we should learn to use the computing cluster, really. You need to know some Unix commands to survive, but you don't really need to know very much Unix. You can get a long way with not very much Unix. I am no Unix expert myself, and I've been working for many decades in these environments. So what I need is obviously enough to survive. To start a job, we need a shell script. So the commands that we could, in principle, have typed directly in the terminal window, We don't do that. We put them in a file and store it as a script, and then we call it a shell script, because shell is the sort of is another word for Unix commands. So this is a text file with some Unix commands. Nothing more than that. It's just like R scripts are text files with R commands, right? Or Python scripts are scripts with Python commands. So there's nothing special about it. It's small programs, you could say, but they are simple. We are many users, yeah, so please behave accordingly. And the system has some administrators that will sort of give you some warnings or throw you out even if you misbehave strongly, or it may kill your jobs if you have done something horrible, and then you will know. So try to be a little bit aware of this, that we are now working together on the same system. Okay.